Okay, in this video, we're going to cover a quick introduction to composition of functions. It's an operation that we really only use on functions, not on numbers. We're going to talk about its definition, how to find its domain, and how to evaluate compositions of functions. And we'll go through a couple of quick examples. This is not meant to be a fully comprehensive lesson on it, but just a bit of an introduction to how to work with this. So the composite function f, and that's pronounced open circle g, so f open circle g of two functions, f and g is defined as, and algebraically we would say f open circle g of x is equal to f of g of x. And that's how it works. So it is this composition. And basically what you want to think of this as is that we're going to put some value into the function g. Then you're going to put that result into the function f. Visually, if I imagined my functions as a couple of little math factory, a couple little boxes here, what I'd be doing is taking some x, putting it into the function g, and I'm going to get some output out of here. And what we do is we call that output very often a y coordinate. You put in an x, you get out a y. But here, because we are using function notation, I'm not going to use a y. I'm going to use the notation g of x. Remember that this notation g of x means the result of putting x into the function g. Then I'm going to take that, put it into the function f. Now, how do I note and write mathematically the result of that? Well, I want the result of what I put into f. So it'd be f with these open parentheses. And what goes in those open parentheses there is what did I put in. Just like over here, I had put an x into the function g, so that x went into those parentheses. In this particular case, I put g of x into the function f, so that is what goes into the parentheses over here, g of x. And that shows just an illustration of what we're really doing. So as opposed to addition, subtraction, multiplication, and division, when I'm finding the two pieces separately, I mean, if you recall, we had f plus g of x equal to f of x plus g of x. And what I'd like to point out here is what we're doing is we're finding f of x and we're finding g of x separately and then adding them together. In this particular case with composition, we're not doing finding the pieces separately. It's like a chain of events. We're finding one and then using that result to complete the second piece. So that's kind of an overview of what composition is. We want to be able to find the domains of these composite functions, and this is can be quite difficult. And so I'm going to write it down, and I'm going to illustrate what it means. So the domain of a composite function is the set of x's, so our inputs, that work in our first function. And it depends on the which function it is, whether it's f open circle g or g open circle f. But they work in the first function. And so the second part of this, and produce results in the second function. Now this isn't a very formal mathematical way of saying it, but it's a start. And we'll illustrate this using the function f and g as defined here. F of x equals the square root of x, and g of x equals 3x minus 7. If I start with, let's say, a value of x, and I'm going to use x equals 2. If I find f of 2. That's the square root of 2. And that's no problem. That's a perfectly acceptable answer. And I find g of 2 I would have 3 times 2 minus 7, which would be equal to negative 1. So that's perfectly acceptable. So what we see here is that x equals 2 is in the domain of f and g. And that's great. But what I'm going to demonstrate in a moment is that while this is true, x equals 2 is not, and I'm kind of jumping the gun here, but I want to tell you, x equals 2 is not in the domain of f open circle g. And that can be kind of tough on some people because they're like, well, if x works in 2 and f works in, if 2 works in f and 2 works in g, how come it doesn't work when you put them together? And the reason is because of the statement we have at the top of the slide here, is that it's about the result that it produces. Okay. Now I'm going to erase the work I have so far. I'm going to make the composition here. Actually, I'm going to just erase what's in black. And we're going to hang on to what is in green here for a moment. Let me slide that over there. So why don't we work with f open circle g? Now f open circle g of 2 would be f of g of 2. F of g of 2. And so what that means is I've got to find g of 2 first. G of 2 would be, since the function g is 3 times x minus 7, this would be 3 times 2 minus 7, which becomes f of negative 1. Well, f of negative 1 would be the square root of negative 1, which would be imaginary and nothing we really want to work with. So we're showing here, and I've got demonstration that while x equals 2 is in the domain of the individual functions, x equals 2 is not necessarily in the domain of the composition of functions. Something to keep in mind there, because it's all about the result. We may have started with x equals 2, but when we got to the function f, we weren't putting a 2 into the f. We were putting a negative 1 into the f. That 2, the number 2, while it worked in the first function, its result did not work in the second function. And so that was bad for us. So we're going to go through some practice, just show a couple of examples really quickly here, and we'll pick up the rest. In your classes. So here's an example here. You might want to take a second to pause the video and write this down. If f of x equals x squared minus 1 and g of x equals the square root of x, find f open circle g of 4, and we're not going to find the domain for this particular one. We're just going to find f open circle g of 4. And so this would be f open circle g of 4 is equal to f of g of 4. So I need to find g of 4. That's the first thing. Work just like order of operations, working inside out. So the first thing I need to do is find that g of 4. The function g says take the square root of my input, so that's going to be the square root of 4. And the square root of 4 is 2. So now I'm going to find f of 2, which would be 2 squared minus 1. So that's 4 minus 1, which equals 3. So that's how we evaluate function composition for a specific value. We're kind of treating it like we do with our other operations, specific and general. All right, so that's a specific case. I'm going to change our view here, make it a little so it doesn't go out on. And now we'll find f open circle g of x. Once again, we're going general in this case, so we're going to find a new function, and then we'll find its domain. So f open circle g of x is equal to f of g of x. Now, for this g of x in this particular case, I don't have a number. So the best thing I can do here is simply to say f of the square root of x, because that's how we defined the function above. And so now what I want to do is I want to take this square root of x and put it into the function. Recall that f of x was defined as x squared minus 1. So now this input right here is what I'm going to put in there. So this becomes the square root of x squared minus 1 equals x squared of x squared is x minus 1. And now we've got to be careful, though, to find its domain. The domain, if I just look at the function itself, it looks like my domain is going to be all real numbers. But I can't do that because g of x does not allow for all real numbers. What I need to do when finding the domain of a composite function is I need to not look here at the simplified version of the function. I need to go up one step. That's a little small there. I need to go up one step and consider the domain pre-simplification. So I'm going to look at what I've got in the box right now and look for my general pitfalls. I'm not allowed to have zeros in denominators. I don't have a denominator at all. And I'm not allowed to have negatives under radicals. So I'm going to look at this piece and say, well, I've got the square root of x there, so x must be greater than or equal to 0, which actually does become my domain. Because I'm not allowed to have a negative value in that spot. And I know it simplifies out, but that's okay. But we don't want to worry about that. So here I'm going to put comma x greater than or equal to 0. So this ends up being f open circle of g. And I know that domain stuff can be tough. Finding the function itself, pretty easy. Finding the domain can be tough. We're going to continue working on it, but this was just one little example to get you going.